Okay. So far we have actually gone into quite a bit of a material in permanent magnet synchronous machines. We looked at the models. How can we transform from stator reference frame to rotor frame? What does the motor look like electrically in that stator frame? How does it change when it goes into the rotor frame? And then the transformation process using reference frame transformation, all that we looked at in the previous couple of lectures. And last time, I think we also looked at the dynamic model, which were modeled through differential equations. And then once all the dynamics settle, what the machine looks like in steady state. So we looked at the two different sets of equations for the same machine. And after that, we started looking at characterization of a permanent magnet synchronous machine, right? Because if you are to do anything, if you want to model, design a controller or any of that sort, you will need to understand the machine you have and what are the characteristics of this before we do that. And for any machine that is being built, if you do need to control properly, the parameters need to be measured. And you may remember some of that from our discussion with the DC motors. Okay. Now, when it comes to permanent magnet synchronous machine, there are a few things that we need to go through to determine or fully understand the machine. First of them is the number of poles. We reviewed that. We went through that last time. So if you want to go back and check that video, feel free to do that. And the next few items we'll try to cover in this lecture. And the methods I'm presenting are not the only method. There are other approaches that we can follow, but this is one type of an approach which I will discuss so that at least you know one of them. I'll briefly mention the other types available to measure these parameters in case you come across them. Okay. And they are fairly similar to the DC machine characterization, but the only twist here is, we have now three phases that we have to work with when we are measuring these parameters. Okay, so you have to be a little bit careful when you measure that machine, measure parameters. Okay, so we've looked at poles. We're good with that. Now the next item is very important, is the phase sequence and polarity. Phase sequence and polarity. Okay, and I won't go into a great deal here, and I won't write. I hope I don't have to write that much here. However, I'll just briefly mention this. Now, phase sequence and polarity, this is something the motor designer will decide. And when you are trying to control the motor, this comes down to whether you define clockwise motor rotation to be positive or counterclockwise positive, because for the clockwise rotation, you will have a certain phase sequence, right? Remember, we talked about this ABC. Once you choose A, B, C sequence for a given motor, when you apply the three-phase balanced voltages or balanced currents, the motor will rotate in one direction. And if you swap the two phases, the motor will rotate in the opposite direction. So it is very important to determine this sequence, right? So you can, let's say we have labeled the windings or the three phases, right? So we have a motor here, and we are numbering them 1, 2, 3, right? 1, 2, 3. So we can choose one to be A, right? Depending on which one is B, we define the motor to be either clockwise to be positive or counterclockwise to be negative. Okay, so that is important, and this is something that you have to identify for that specific type of or class of motors that you're going to use, and you have to stick to it. Unless all the control functions you design may not function as expected or not function at all. So that's one important. So your phase sequence selection, ABC, uh, is something that you do need to choose. And I'll talk about how we do that. And then the other thing is, when you determine polarity, whether it's clockwise or counterclockwise, now we have the question, okay, is it clockwise when you are looking from the front or from the back, right? This is the other standard that you have to think of when you establish this motor polarity concept. Okay, and it is up to you to choose what that's going to be and what that needs to be. And then typically, a rule of thumb, this is not a very strong, strong rule that I'm forcing you to follow, but typically you will see a motor position sensor, right? Maybe it's an encoder, maybe it's a resolver, maybe it's a hall sensor that gets mounted here, right? Let me use a different color for the position sensor. Okay, so we have a position sensor and you have wires coming out, right? This is basically giving you the position. Now, if you have the position sensor mounted and you can measure position, one thing you can do is you can choose, when you look at the motor position, when the motor is rotating in a certain direction, you're going to see the position vary like that. If the output, is a linear output. Some sensors have sine, cosine, but we're not talking about that. Those sine, cosine signals can again be converted into this ramp signal, which is the position signal. Okay, and then when you rotate in the opposite direction, guess what? You're going to see the opposite slope, right? And these are not aligned, by the way. I'm just showing you the slope, the difference in the slope, right? Now, what I would follow, I would say I apply a certain phase sequence and I see positive slope of the sensor. I'd be inclined to call that positive polarity, and then you can look at from the front of the motor and see, okay, is it going clockwise or counterclockwise? That is my ABC sequence. Okay, the reason is when you have a positive slope, that gives you positive speed, right? When you have negative slope, you'll have negative speed, because rate of change of position is speed, angular speed, right? So that way, you kind of have an established direction for that type of motor. There might be people that will disagree to that, but I'd say this is what I would follow in order to establish this motor polarity concept for a given type of a motor. Now, in order to set up in this order or in this phase sequence, if you have a position sensor, okay, you can monitor the position sensor. You will have to rotate the shaft with another motor or another power tool that you can attach to the shaft. Make sure it's stable, the machine is bolted down so it doesn't move around, and then you'll have to find some mechanism to rotate this motor in a certain direction, right? And then you can look at how you can measure the voltages coming out from these three phases. So you'll probably need isolated probes so that you can measure the line-to-line voltages. Okay, line to line, here to here, and here to here. So basically, you are measuring the line-to-line voltages coming from the motor, because since this is a permanent magnet motor, when you rotate the shaft with another machine, some kind of a mechanical means, you will see voltage build up because of the permanent magnet, right? This is your back EMF. So now in this case, what you can choose is, depending on how the voltages show up, you can arbitrarily select a phase to be A. Okay, I'm going to say, hey, this is my phase A. All right. And now you can see the three voltages, right? So let's go to different ways. We are looking at the different line to line voltages. So let's say we see one voltage like that. And then you see another one like that. They're going to be 120 degrees apart. This is not 120. So this should be about, to make it a little bit more accurate. So let's say if you look at your oscilloscope, right, you're going to see these three line-to-line voltages. Okay. Then, so you have three phases here, right? You haven't named them yet. So this may be from 1 to 2. This is from 1 to 2. It's 1 to 2. This is probably 2 to 3. This is 2 to 3. And this may be 3 to 1 or 1 to 3, right? And depending on how you choose that, you will see a difference. Now, this is if you don't have access to the neutral point. If you have access to the neutral point, you can directly measure the voltage to the neutral point, or from the neutral point to a phase. So if you have access to this neutral, now you can measure these voltages independently and look at the phasing of them. Okay, so once you see these voltages, you can select 1 and 2. Okay, so you can name first one A. Okay, that corresponds to 1. Okay, so from that, if you look at B to C, this is going to be again 120 apart, right? So we'll call this B, and then you can call this C. That's how the phase sequence will work out. Okay, so does that make sense? How to go about choosing your phase sequence based on the back EMF? Because if you look, let's say we have VA, VB, VC to be VS, or we will say sine omega t, V sine omega t minus 120, V sine omega t minus 240. Now, if you are to look at VAB, this is basically V sine omega t minus this term, right? Sine omega t minus 120. Now, if you solve for this and look at the phasing of VAB with BC with CA, you will see that all three are again 120 degrees out of phase, which are these line-to-line voltages. Okay, which are these line-to-line voltages. So that way, using that line-to-line measurement, now you can establish your phase sequence. Another difference you'll see that in most cases, you will see 3 to 1. You'll see that in certain cases, when we because we are kind of going in with a blind eye, right? So you have your 1 to 2. This becomes 3 to 1. Okay, this is 3 to 1. And then you'll have 2 to 3. Okay, so this is 2 to 3. This is 3 to 1. this is 1 to 2, right? So the voltage differences. Now, in this case, you can see that you can choose this one to be A, and then when you are to go and select B, you can clearly see that the phase difference between 1, 2, and 3, 1 is 120 degrees, right? Therefore, in this case, 3 becomes B and 2 becomes C. Okay, so that's the importance here. That those are the only two combinations you could see in this case. Okay, because we are choosing 1 to 2 to be A. All right. And sometimes you can even see worst case, even like a little bit more different. You could see 3 to 1 here. You could see 1 to 2 here, and then 2 to 3 here. So first of all, start with selecting one of them, name that first one A, and then look at the relative phasing between them to name the rest of the phases. Okay, that way you can name ABC sequence for that chosen direction of rotation. Okay. So we have the direction of rotation done. That's one of the important characteristics that you need to know before. It's not necessary for modeling, but it's important for your controls to set up your sensors and establish the directions of rotation. Okay. All right. So next is to measure resistance. All right. Next we're going to go measure flux linkage. That's important. Flux linkage. Okay. So let's see how we can look at flux linkage. This is similar to the back EMF constant. Okay. So call this flux linkage or back EMF constant. Back EMF constant. Okay. Now this is also relatively straightforward. Can you propose a method to find this back EMF constant? I'm sure you can come up with an idea for this. Let's see if you can. What do you guys think? How can we measure back EMF constant? Okay, so now remember, yeah, go ahead, Lucas. So how did we measure the back EMF constant of a DC motor? These things need to come, like, you guys need to remember, DC motor is like, it's in the past now. Okay, right, that's true. But how do we measure KE? How can we measure KE? So you can find KT at stall, but that requires you to measure torque, right? We need to measure torque, we need to measure the current, and then we can find the total, because the stall condition is very difficult to measure torque because it's you can still measure, but there's no rotation, right? So you can use the data sheet, but let's say you don't have a data sheet, you have just the motor, then what can we do? I'm trying to find the right word. Because stall condition, you lock the rotor and then apply current. So how much current can it handle? We don't know that, right? You can apply the rated current and then measure torque there and then find KT, but that becomes a little bit tough. You need expensive measurement schemes for that, sensors, right? But how about this? We spin the motor, right, at a known speed, okay? And then once the motor is spinning, what can we see across the phases? Exactly, back EMF, right? So similar to the previous case, right? If you can spin the motor maybe at the rated speed, and we can measure the line-to-line voltage, right? So you'll see that. So now you have named your phasors. Okay, so this becomes VAB, right? So you have named it, and then we have our VBC. Okay, this is VBC. Then we have our third phase, VCA. Okay, so you have measured them, right? You can do this at the same time as you do the the phase sequence, right? You can do both at the same time, and from this you can even find the frequency, right? See, you can find the frequency. So you have an idea about the motor speed because you know how fast the motor is rotating based on the electrical frequency and number of poles, right? Because number of poles we found previously. So you can kind of knock all three at one test if you have a good position measurement to see measure zero crossing. All right, so now we have VAB, VBC, VCA, and you want to have it run at a steady state speed so that there's no fluctuation. And for a good motor, well-designed motor, these peaks are going to be identical. Okay, there might be slight variation, but in general, they're going to have the same peak values, which means they are of the same amplitude, right? And then for each of these, we can write the relationship VAB, VBC, VCA, right? We can say, let's write this as a vector, it's easier. This becomes root 3 lambda m prime r, don't need the r, omega r. This becomes cosine theta r plus pi over 6. This becomes cosine theta r plus pi over 6 minus 2 pi over 3, just 120 degrees, right? So this is here. Here cosine theta r plus pi over 6 minus 4 pi over 3, right? So you have the three phases, and then once you measure this peak value VAB is equal to root 3 lambda m prime r omega r. We know omega r from the frequency and the number of poles, root 3, and the only unknown becomes this, and now you can calculate for that. If they are different, you can even find an average value based on each of them. Okay, so this is a good estimate, not estimate, but for linear region, this is a good flux linkage value. But depending on different nonlinear characteristics at saturated or beyond saturation, or beyond that boundary between linear and nonlinear magnetic saturation point, you will see that the characteristics of lambda m change a little bit. So you have to be very careful. This is only for that linear region. For nonlinear operation, you can characterize to more extent and come up with these nonlinear curves for magnetic properties. And that's a little bit more outside the scope of our discussion here. This is a very simple way of coming up with that linear value, lambda m prime r. Okay, so we have our flux linkage or the back EMF constant for the permanent magnet synchronous machine this way. Okay, all right. 3 down. So we have what? We have the phase sequence taken care of, flux linkage, back EMF constant taken care of. We need to measure resistance. Very easy, right? So this is a DC resistance of the machine, DC resistance. And depending on the design of the motor, sometimes these resistance values are very, very small, less than 1 ohm. So you want to be very accurate in the measurement scheme. Okay, so for that, what we typically do is we use the 4-wire measurement. Okay, we use 4-wire, so measure line to line resistance using 4-wire measurement. 4-wire measurement. Okay, maybe you remember this from your 235 class. Okay, what we basically do is we have a 4-wire system where we have an amp meter connected. Okay, you're gonna see some resistance from the wire, call this R wire, and then you'll have your motor phase or the line to line. So let's say this is phase A. You're gonna have 2 resistances, right? Because line to line B, and then phase C is kind of open. See, I'm not drawing the inductance and the back EMF here. And then you have some wire resistance here again, wire. So you have this voltage. So typically the device will do that, and there are dedicated devices that does that. And then you measure the voltage drop across that line-to-line connection. Okay, and then what you'll basically get is you'll get R. So we'll call this R of phase A. This is R of phase B. And typically they are almost the same in value, so it's okay to find the total value and divide by 2 unless there's a fault or some kind of a very bad design. Okay, generally they're pretty close. And then now you know your V, right? Now you know your current, you know your voltage drop, you know your current. You can find using V equals IR. You can find your R equals V over I. Okay, so this is a very high accurate measurement scheme that you can use. Now, what's the other way to do this? Well, you can place your voltmeter here, or you might want to use the voltage that you're supplying. Or if you move your amp meter in here, right? If your amp meter in here, now all these will add some resistance to the measurement. And that way your voltage measurement might have some error, and it will carry over to your motor resistance value and might make it incorrect. So that's why we try to have the amp meter before the voltmeter. Okay, so this is a 4-wire resistance measurement scheme, and now you can find your phase resistance this way. Okay, good. All right, so we have our resistance measurement done. What else we have? We have the inductance. Okay, these are the ones that are a little bit tricky and probably a little bit tricky to understand what they mean. So just hopefully, follow the method in general, and then if you try to think about it offline, and you might be able to understand what we are trying to do. First of all, I'll go through the process, and then I'll try to explain the mechanics behind it. Okay. So first of all, we'll go for d-axis inductance, the direct axis inductance. Now, keep in mind, there are LCR meters that you can use to measure d-axis inductance, but some of them are very low current. And the problem with them is you are not capturing the full flux linking through all the winding and the material, because there's no flux building up when you measure inductance. Okay, so you have to be a little bit careful when you use those measurements. Sometimes they are inaccurate depending on the current and the design of the machine. Okay, all right. D-axis inductance. First of all, you're gonna decouple the machine from any other load. Decouple the machine from loads, if there are any loads. Okay, and then we're gonna connect phases B and C together. Okay, and then once you connected B and C together, then you will supply a current, a DC current, that is less than the rated machine current to the machine. Okay, now what I want you to think about at this point is, okay, why do we do this? Okay, what will happen when we apply DC current to this AC machine? This is what I want you to initially think about. So I'm going to draw what this will look like. And in the meantime, I want you to think about what is actually happening. Okay, give me some ideas. Why is this going to help us measure our d-axis inductance? Okay, so let's say okay, so this is what we do. We apply, let's call this I, and then the current goes through and comes back, so the total current I will return. Okay, so this current direction is important, going through A, coming back from B and C. Why is it important? That is the key question here. Let's see. Let's look at our machine. Okay, so now let me draw our stator here. We have A, this is A prime, and we called B prime. So I remember, so B, and then we had C, right? Somewhere here, maybe C and C prime, right? So we have our phase sequence. Now I'm not drawing the rotor yet. All right, so when we apply positive current through A, right, so current is going in through A. All right, current going through A. And if so, we are applying the current going in, obviously the returning current is going to come out like that, right? And then that current, that DC current, is returning from B, right? The DC current is returning from B. I'm trying to think if this is the best way to show this. Let's see. Let's see what we get. So B. So the current here is this way. This is returning. It's like that. Here, like that. Okay. So let's see if this this gives us where we want to get. Now, when we apply current this way, what can we say about the flux that builds up due to A from the stator? So based on the right-hand rule, the flux is going to be from A, it's going to be in this direction. From B, it's going to be in this direction, right? And from C, it's going to be in this direction. Okay. Oh, very nice. This is convenient. Now, if we look at the total, the resultant flux, right? So the vertical components of B and C, right? They will cancel each other out. So the total flux vector from the stator will be pointing in that direction, right? From the stator. Okay, so that is like having a north and a south. North and a south. Okay. Is that clear? Having a north and a south like that. And then now let's think about our rotor, right? So the rotor, if we think it has, you know, I'm going to just arbitrarily draw it like that. So let's say we have a north and a south. What would, so let's have a little bit of a saliency to show what's going to happen here. There's a bit of saliency there. How will this rotor magnet align given this condition? How will the rotor align? Okay, exactly. So your north, so your rotor will be like this because it will align with the south of the stator, right? So this is my flux of the rotor. This is my flux of the stator. These are DC, right? These are DC fluxes. It's going to stay in position like that. Okay. All right. So that means my rotor will align in this orientation, right? So it's gonna align like that, north and south. Okay. All right. You guys with me? Okay. All right. Now, this is very important. If you think of the direct axis, right? When we called direct axis, what did we define it as? Direct axis, we said we call it a direct axis for a reason. Why is it called a direct axis? When we align the direct and the quadrature axis, we had a reason behind it, right? What is the reason for choosing the direct axis in a certain way? We had a reason behind it. Okay, I don't know if you remember that. We said we'll choose the direct axis such that it's going to be along with the rotor flux, right? It's direct with the rotor flux. Now, if you look at this arrangement, right? So you have your permanent magnet rotor aligned in this way, and your windings are like that, right? A, B, and your C, right? So those windings are like that. And now we have, by using this DC current, we have forced the rotor to align in this direction such that when we measure inductance from A to B and C, we are measuring the inductance considering the material along this direct axis. Okay, so it's going to capture the flux flowing through this. Okay, how do we do that? I'll get into that. Okay, this alignment is important. Okay, all right, so that's kind of the mechanics behind it, why we apply the DC current to orient the rotor in this way. Once we do that, so now we have applied that, we have some more steps to follow to take the measurement. This is basically applying the voltages. Now at this point, we can either, once it's aligned this way, you can lock the shaft. You'll need some other means, another machine or another like a wrench or some kind of a physical mechanism to hold the shaft in a stall condition. And you can apply a step input. You'll see a certain transient, right? Remember from your experiments, right? Once you apply a step voltage input, very small, you're going to see your current flow in a certain way, right? And then you can use the time constant, the tau, to find the inductance, right? That's one method. You can use that as one method. Alternatively, what you can do is, and this is kind of the standard practice, once you have aligned with the DC current, lock the rotor, right? Lock the rotor so that your motor, the rotor alignment does not change from this. It cannot change. Okay, once you lock the rotor, lock the shaft in place with respect to the stator, so the stator can't move either. Okay, now we will measure impedance from phase A to phase B and C. You're not going to remove this connection, right? So once you're done this, you lock the rotor, you measure impedance between these 2 points. Okay, so once you measure that, we'll call this Z A to BC. This can be written as RS plus J omega LD. You have your D-axis inductance. Okay, so you can measure it in couple of different methods. You can apply a lot of current, like a high current step. You can measure the time constant, or there are other like a sinusoidal injection methods to measure the inductance too. Okay, and that way you can obtain the inductance at a certain frequency rather than the time constant or the steady state value. Okay, we can do that at different frequencies. So now this will give you your D-axis inductance. Very convenient. Okay, all right. So we have our D-axis inductance. So let's see what we have here. So we have our D-axis inductance. Now the only thing left is for Q-axis inductance. Okay. Can you propose a Q-axis inductance measurement scheme? A way to measure Q-axis inductance. Okay, so there are a couple of different ways you can apply currents in a different direction, different phase sequence to align the rotor. But there's a very easy method to do this. Okay, so you have already locked your rotor to measure what? Measure d-axis inductance, right? So we'll leave it at that. So inductance, we leave it at that locked rotor condition. Okay, so lock the rotor as for measuring d-axis inductance. Okay, and then instead of measuring from A to B, instead of measuring from A and to BC, right, we will measure impedance from what? From B to C. Okay, so I'll show you what we're going to capture. Measure impedance from B to C. Leave phase A open. Okay, so you're basically leaving phase A open, and what that does is you're going to leave your rotor in the same orientation. However, you're going to measure from these two to these two, which is going to capture this axis. This is the quadrature axis. Whether you measure it from here to here or here to here, the inductance is only capturing the material. Therefore, your inductance value will remain the same. It's a scalar, right? So you're going to measure that inductance. So you can actually simplify the process here. Okay, so now you can measure ZB to C, which will give you again RS plus J omega LQ. Okay, you'll get the inductance. So again, you can apply a step input and then look at the tau, and then you can calculate it that way. Now again, be careful. RS here is you are using two phases, so you have to adjust. Consider that RS value when you do the calculation appropriately. Okay. However, the inductance doesn't change. Right? This is the Q-axis inductance, and once we know LD and LQ, we know how to convert that to our LM, and then what was that? Self-inductance and mutual inductance, right? Half of LM, general speaking. Okay, and we've talked about that process earlier. Okay, so we have all our parameters, right? We have all the parameters. We're good to go now. So now you can go and design a controller. You can evaluate your motor performance, all that kind of things. The only thing that I haven't discussed here is the nonlinearities like magnetic saturation. That's a little higher level concept, and I don't want to get into that at this stage. Okay. All right, so you guys now know how to characterize permanent magnet synchronous machines. Any questions? Any questions? Okay, so let me